we're going to take our English projectile homework and just kind of go through these questions. So number 10, we have a quarterback hiking a ball from the center. 3 seconds later, he passes the ball downfield with a velocity of 20 meters per second at a 30-degree angle. Okay. So it's throwing that ball at 30 meters per second. Oops, sorry, I got that backwards. 20 meters per second at a 30-degree angle. Okay, so the first thing we want to find is how high does the ball travel? So here we are trying to find that maximum height. So if we're looking for the maximum height, that's a vertical value. So it makes sense we would want to look in the y direction to find that maximum height. So we want to see what values we know in the vertical or in that y direction. Okay, so we know when we are looking vertically, our acceleration is always going to be from gravity. That's going to be our negative 9.8 meters per second squared. Since we are looking at the maximum height, we also know that our final y velocity, and remember that's just in the vertical direction, but that our final y velocity is going to be 0 meters per second. Because vertically, that ball needs to stop in order to move back down. Still moving horizontally, but that vertical final velocity is 0 at the maximum height. And then using the information here, we can also find what that initial y velocity was. So how much that 20 meters per second was directed vertically. Okay, so in order to find that initial y velocity, we're going to use sine. So do 20 sine 30, and that'll tell us our initial y velocity was 10. So using this information, I want to find my maximum height, or in this case, my delta y at the top. I do not know my time to reach the maximum height. Okay, that 3 seconds, the quarterback is still holding onto the ball. So that 3 seconds does not include the time that the ball was in the air. Okay, so using this information, I'm going to want to use my equation that my final velocity squared equals my initial velocity squared to a delta y. Okay, because I know my final y velocity is 0. We found my initial y velocity was 10. Plus 2 times the negative 9.8 times that delta y, which we're trying to find. Okay, we're trying to find how far vertically it travels. So from here, it just becomes an algebra problem. Okay, so subtract the 10 squared on either side, then divide by 2 and the 9.8. And we should get that delta y, and that maximum height is 5.1 meters. Okay. So then looking at the next one, here we're looking at our entire time of travel. Okay, we're trying to find how long the ball is in the air, so the time to catch the ball if it is caught at the same height it was thrown at. Okay, so here we know if it's caught at the same height it was thrown at, that tells us that our delta y is 0. Okay, because it's starting and its ending position at the same height. Okay, so we're gonna again want to look in the vertical direction here because that's where we know the most information. We know our vertical displacement. We know our acceleration is negative 9.8 meters per second squared. And we know when that ball was first thrown at an initial y velocity of 10 meters. So given that information, we want to find the time that it takes to catch the ball. So from here, we want to use the equation that delta y is equal to initial velocity times time plus 1/2 at squared. So we know our delta y is 0, our initial y velocity is 10, and then plus 1/2 negative 9.8 t squared. Okay. Since we have a t and a t squared here, we're either going to use the quadratic formula, or you can factor out a t. Either way, when you do that, you should find that your time is 0 and 2.04 seconds. So we're going to want to take our 2.04 seconds. So we know the ball is in the air for a total of 2.04 seconds. So then using that information, we want to see how far downfield the ball travels. So here we're trying to find our range. So what is our horizontal displacement? So here we need to look horizontally. So we know that we can find what our initial horizontal velocity is. Initially, out of that 20 meters per second, how much was directed in the x direction? So use cosine there because we're looking for the adjacent side of that triangle. And we'll find that initially our ball was moving horizontally at a rate of 17.32 meters per second. Careful. When you're using your velocity in these equations, you never want to use the 20 because we're only looking in the horizontal or the vertical direction. We never want to use that overall velocity. Okay, but I know to find my range, I'm also going to need to use my time. And we found in the previous question that it takes 2.04 seconds for the receiver to catch the ball. Okay. So from here, I'm going to use my range equation. Remember, I don't have any acceleration in the x, so I can drop the 1/2 at squared. So it's 17.32 and 2.04. And I find that he is going to catch the ball 35.33 meters downrange. Okay. All right. So then in part D, we want to find what average velocity does the receiver have to run in order to catch the ball. So we know our equation for average velocity from Jeff. And remember, this was displacement over time. So that receiver is running horizontally. So we want to look at our horizontal displacement. So we know our ball had to travel 35.33 meters. So that means our receiver is also going to have to travel 35.33. We want to divide that by the total time. So here, this is where we need to kind of go back to our original problem. So we know the quarterback has that ball for 3 seconds before he throws it. And then when the ball's in the air, it takes 2.04 seconds for the receiver to catch it. So to find the total time of the play, we're going to take the 3 seconds before the ball was thrown plus the 2.04 seconds that the ball was in the air to see how much time the receiver had to run. So we do our 35.33 divided by our total time of 5.04, and we'll find that he needs to run an average velocity of 7.01 meters per second. Okay, so we skipped number 11, and we're going to take a look at number 12. Okay, so here you and your friend are standing on opposite sides of a canyon. You're playing catch with the football. After a while, your arm is starting to get tired. You know the canyon is 20 meters wide. Okay? And you're going to throw the ball at 12 meters per second at 35 degrees. So you know you're throwing that ball at a velocity of 12 meters per second, at an angle at 35 degrees. So we want to see if the ball makes it to the other side with that velocity. Okay? So what we're going to do is we are going to take a look to see how long would it take your friend to catch the ball. So we're going to start this off like we would any other problem. What information do we know horizontally and what information do we know vertically? Okay. So since we know our velocity, we know we can solve for those initial x and y components by using our trig function. Okay, so we can use cosine to find that initial horizontal velocity. So 12 cosine 35. And we are finding horizontally, our ball is traveling at a rate of, my pen decided not to work, 9.83 meters per second. We're going to do the same thing in our y direction, but here we're using sine because that's the opposite side of our triangle. And here we'll find that our ball is traveling vertically at a rate of 6.89 meters per second. Okay. So what else we know is looking vertically, we know our acceleration is always negative 9.8 because we always have that force of gravity acting down, meters per second squared. And we're trying to find if the ball makes it to the other side of the canyon. So this is a little tricky. So we do not know for sure that that ball is going to travel the full 20 meters. But what we do know is if your friend is going to catch it, that means your delta y has to be 0. Okay? So we're trying to find out if our range is actually the 20 meters. Does the ball make it over? So we do not know that value for sure. Okay? But we do know if your friend catches it, that tells us our delta y has to be 0. Okay. So looking at this information, then what we can do is if we want to find the range, we need to find our time first. So we're going to look in that vertical direction to find time. Okay, how long would it take your friend to catch the ball? So delta y is equal to initial velocity times time, your 1/2 at squared. Delta y is 0, initial velocity is 0.89. Our solution is 9. So we find if your friend catches the ball, again, we're going to have to use quadratic formula here. It would take the ball 1.40 seconds to reach your friend. So we want to find, with that time, does the ball make it over? So we'll look at our range equation. That delta x is equal to our initial velocity times time. So we'll do our 9.83 as 1.4, and we'll find that horizontally, our ball travels 13.76 meters. So our ball only makes it 13.76 meters. It does not make it the full 20. So it does not make it to the other side of the canyon. Okay, because it only travels 13.76 meters when it needs to travel 20. So in problems like this, okay, you kind of want to look to see what do you know has to be true, and then does that match up with your scenario? Okay, so we did not know that that ball for sure was going to travel 20 meters, so we could not use that originally. Okay. And then for B, what we want to find is, since it does not, how far down the canyon wall does it hit? Okay, so here, we know it's making that full 20 meters, looking horizontally. And we want to see when it travels that full 20 meters, what's its vertical position? Okay, so we know that range is 20 meters, and we know our horizontal velocity is 9.83 meters per second. So using our range equation, we'll find that our ball is in the air for a total of 2.03 seconds. So it takes 2.03 seconds for the ball to reach the other side. We want to see after those 2.03 seconds, what is our vertical position? Okay, so vertically, we knew our initial y velocity was 6.89. We know our acceleration is negative 9.8 meters per second squared. Now we also know our time, and we want to find our delta y. What's our vertical position? So use our delta y, initial velocity times time, 1/2 at squared. Plug in what we know. We'll see what our vertical position will be once that ball does get across. If you wanted to, you could also solve part A this way. Okay, because you would see once that ball does travel the full 20 meters, its vertical position is going to be negative 6.28 meters. That means it's going to land 6.28 meters below the edge of the cliff. Okay, so it didn't make it fully across. It landed beneath the edge of the cliff. Okay, so if you wanted to, you could also solve part A that way. Okay. Jump through a planning area. The landing ramp do not match up. The landing ramp is 25 meters high, and the takeoff ramp is 10 meters high at the end. Okay, so that means here, if this is only 10 meters, and we're ending 25 meters above the ground, our motorcyclist is going to have to travel 15 meters upward. So we're going to have a displacement of delta y here. So our goal is to find how long the rider is in the air. So we just saw that in the y direction, we know our delta y has to be 15 meters. We're ending 15 meters higher than where we started. Vertically, we also know that acceleration is negative 9.8. And we're also given this information that we're traveling at 45 meters per second at an angle of 25 degrees. So we can also solve for that initial y velocity by using sine. 45 sine 25, and we'll find that the motorcyclist is in the air, or sorry, has an initial velocity of 19.02 meters per second. Okay, so here we want to find how long it takes the rider to reach the top of the other ramp. So if we know delta y, our initial velocity, we're trying to find time, we know our acceleration, we're going to want to use this equation. So we know delta y is 15, initial y velocity is 19.02. This one we are going to have to use the quadratic formula. Remember, your a term is always the one in front of your t squared, the b term is the one in front of the t, and the c is the one without the t. Okay? So when we use that quadratic formula to solve, we are going to find that it takes the rider 2.78 seconds to get across. Okay? Careful for these ones. You cannot just assume that he reaches the other ramp at his maximum height because we don't know what the maximum height is. But what we do know is that he's going 15 meters up, okay? And we cannot assume that that's going to be the maximum height of the rider. So do not use your maximum height information there. So then for part B, we want to see what's the horizontal position of that ramp should be. So we're trying to find the range of that rider. So here, if we want to find a range, we need to find our initial horizontal velocity. So do 45 sine 25. And we'll find initially, he's moving at a rate of 19.02 meters per second in the horizontal direction as well. Okay. So to find our range, we do our delta x equals initial velocity time. And so we'll do 19.02 as our initial velocity times our time of 2.78. And we'll find he's trying to travel a horizontal distance of 52. Oops. Let's go back. Over here, I put in 45, not 25. That's bad, my bad. 45 sine. Oh, that's what I did. This should be cosine. Oops. Because we're looking for the horizontal component, the adjacent. So 45 cosine 25. There we go. So this should really be 40.78. There you go. So make sure you're paying attention to those trig functions. And that means that our range then would be 113.38 meters. So that landing ramp would need to be placed 113 meters away from his takeoff ramp. Time that the ball's in the air. The key here is that the football is kicked off the ground and returns to the ground. So that tells us that our delta y is 0. And then we're trying to find the time. And since we know more information vertically, we want to look at that y direction first. Should find that the ball's in there for 2.26 seconds. All right, so this one may bring some PTSD back to some Bears fans. But so in this one, we have Cody Parkey, who is lined up for a game-winning field goal over the Eagles. We know the field goal posts are 35 meters away. Okay. And he kicks the ball at 20 meters per second at an angle of 40 degrees. Okay. So the first thing we want to do is find our x and y components. So this is where we're going to want to use our trig. Looking horizontally, or the x component, that's going to be our adjacent side. So here we'd want to use cosine. So do 20 cosine 40 to get that horizontal component to be 15.32 meters per second. And then to get our initial y velocity. This then is that vertical component. So here we're going to want to use sine. So 20 sine 40. And we'll find that our initial y velocity then will be 12.86 meters. Okay, and these are the velocities, again, that we're going to use in those equations. In our equations, we're never going to use the 20. Okay, so we know the field goal posts are 3.05 meters off the ground. So we want to see how long it would take the ball to reach a height where it would go over those field goal posts. Okay, so here we're looking at a vertical height. So we know our delta y is 3.05. We also know our initial y velocity was 12.6 meters per second. And again, vertically, we always know the acceleration is 9.8 meters. Okay, so we're trying to use time and find time, and we know our delta y, our initial y velocity, and our acceleration. So we're going to want to use this equation. Our delta y is 3.05, our initial y velocity is 12.86, and that acceleration is 9.8. Again, this is one where we're going to have to use our quadratic formula, so I know. No fun. But so when we solve this, we're going to do 2 times. We're going to get a time of 0.264 seconds and 2.3 seconds. We need to decide which one we want. And to decide this, it kind of helps to look at the motion of the ball. So when Cody Parkey kicks the ball, it's going to come up first and then back down. Okay? And we want to find the time that it takes to reach a height of 3.05 meters. So notice, it's going to reach this height twice. It's going to reach it once on its way up and again on its way down. Okay? We know that the ball will actually go through the field goals potentially when it's on its way down, and not when it's on its way up. So that means we want to take the time for the ball's motion when it's on its way down for that second time. So we're going to take the 2.36 seconds here. Okay, because that's the second time, that's when the ball is on its way down. Okay. Then for C, we want to find the range of the ball in this time. So here we're looking horizontally. Okay, and we know our initial x velocity was our 15.32. And now we also know that it takes the ball 2.3 seconds to reach those goals. So do delta x equal to initial velocity times time. So do our 15.32 times time of 2.36. Here we'll find that the ball has a horizontal displacement of 36.16. Okay, so what that tells us is that actually when the ball reaches a height of 3.05, it's really past those field goal posts. Okay, since it reaches height past the field goal post, it does travel at least 35 meters. So theoretically, he should make it. Okay. If you guys watched that game, you know in actuality, he did not. He joined it off the side of the post. Womp womp. Yes, theoretically, he should have been able to make it, but was not the case in actuality. So that's kind of a bummer. Here we have a sphere traveling at 20 meters per second. They're launched off a little hill at an angle of 30 degrees. Okay. And they say they hit a tree when they're at the maximum height. Okay, so here we do know that that sphere is actually traveling to its maximum height. Okay, so since we're looking at the maximum height, we want to look in that y direction. Okay, and we know vertically our acceleration is always -9.8 meters per second squared. That's a given. Since we're at the maximum height, remember that final y velocity then is 0 meters per second. Because at that maximum height, all of our velocity is entirely horizontal. Okay, there's no vertical component there. And then since we know our initial velocity and the angle that it's at, we can also find that initial y component, the initial vertical velocity. Again, our y's are opposite, so we're going to use sine here. So 20 sine 30, I believe it's going to give us a 10, but let's check. Yep, in meters per second. Okay, so here we're trying to find the time. How long was he in the air? So in this case, we're going to use a little bit different equation. We're going to use our final velocity is equal to our initial velocity plus acceleration times time. Because we know that final velocity is 0, our initial velocity is 10, and that acceleration is negative 9.8. Okay. So here we'll do some algebra and we'll find that it takes us here 1.02 seconds to hit the tree. How fun. Okay. So then for B, we want to find what the maximum height is. Okay. So we can now use our time that we solved, or we can stick with the original 3 values that we know. We really have a variety of equations we can use here because we know all of our other values. Okay. But if I just stick with what we were given for part A, we can use the equation. Our final velocity squared is equal to our initial velocity squared plus 2a delta y. Because we knew our final velocity was 0, our initial velocity was at 10, and our acceleration is always negative 9.8. And we'll find that our skier friend here reaches a maximum height of 5.10 meters. Okay, so we'll end at 5.10 meters above the ground. So then for C, here we're trying to find our range. How far horizontally does our skier travel? So here we'll use our equation of initial x velocity times time. We already found our time in 16a. We know to get our initial x velocity here, we're going to use cosine. So 28 cosine 30, because that's the adjacent side of our triangle. And we'll find initially he's moving horizontally at a rate of 17.32 meters. We'll take that 17.32 times the time that we saw from part A. And we'll find that he travels 17.67 meters horizontally. Okay. Drawn below the horizontal. Okay. So we're throwing the rock down initially. So we'll start off like we would any other problem. Horizontally, we know we can find our initial x velocity because we know our velocity in the angle. We'll use cosine because that horizontal component is going to be adjacent to that angle. And we'll find that our initial x velocity is 38.97. Okay. So then looking vertically, here again we can find our initial y velocity. And here it'll be sine 30. The trick here is that since we're throwing it down, okay, initially the ball has a negative velocity. It's moving downward. So we would do negative 45 sine 30. I get negative 22.5 meters per second. Okay, because we're throwing it down, the vertical component is going to be negative. Okay, but then we always know that our acceleration in the y is negative 9.8 meters per second squared. And here, we know that the ball is moving 42 meters downwards, so our delta y would be negative 42. So here we know more information in the y direction. So that's the direction we're going to look at to find our time in the air. So we'll use this equation because we know our delta y is negative 42. We know our initial y velocity is negative 22.5. And we know our acceleration is negative 9. Okay, so when we do that, we should find that it takes the ball or the object, the rock, 1.42 seconds to hit the ground. Okay, so then B, now we're looking horizontally. We want to find our range. We need to use the initial x velocity times time. We already found the initial x velocity to be 38.97 times our time of 1.42. So we should find horizontally, we will have a range of 55.34 meters. This value is still going to be positive because we're still moving to the right. Okay, we're still moving in the positive direction horizontally. It's just our vertical that's negative. Okay, so see, here we want to find our velocity at impact. This one is a little tricky. We want to find what our velocity is when we hit the ground. So we're trying to find, basically, again, we're always looking for triangles, a hypotenuse of that velocity. Okay, what's that velocity at an angle? So what we're going to need to do here, since we want to find the hypotenuse, we're going to have to look and see what are our final x velocities and our final y velocity. Okay, let's redraw this down here. Thankfully, we know our velocity never changes in one direction, and it never changes in that horizontal direction, okay? Because we don't have any forces or any acceleration horizontally. Okay? We do need to solve for that final vertical velocity, because there we do have accelerations, so our y velocities are going to change. Okay? So looking in the y direction, we knew our initial y velocity was our negative 22.5. Okay? And we know that our acceleration is negative 9.8. And we now know that it takes 1.42 seconds to hit the ground. We could also use our displacement. Okay? But since we know these three variables, we can use our equation. Final y velocity is equal to initial y velocity plus acceleration times time. And we will find that our final y velocity right before we hit the ground ends up being negative 36.42 meters. Okay, so we can put negative 36.42 on the y component of that triangle. Now it turns out nice and easy because we know two sides of our triangle. So to get the hypotenuse, we know we can use Pythagorean theorem. So we can do 38.97, the x component squared plus that vertical component, negative 36.42 squared is equal to our velocity squared. And we'll find that we have an overall final velocity of 53.34 meters per second. Okay. Be careful here because since it's squared, you'll always get a positive value here. But since your rock is moving down, again, we want to make that value negative. Throwing a rock off a tall building at 45 meters per second at an angle of 60 degrees above the horizontal. So here, since we're looking at our max height, that's a vertical value. So we're going to want to look to see what we know in the y direction. Okay, so vertically, we know our acceleration is always, let's see. Our acceleration is always negative 9.8 meters per second squared. Since we're at the maximum height, again, that final y velocity is 0. And again, that's just the y velocity. We're still moving horizontally. And then we also know our initial y velocity because initially we're moving at 45 meters per second at an angle of 60. So we can use sine to find that initial vertical component to be 38.97 meters per second. Okay, so here if we want to find that maximum height, knowing our final velocity, initial, and acceleration, we can use the equation that our final velocity is equal to our initial velocity squared plus 2 times our acceleration times delta y. Because we know our final velocity is 0, our initial velocity is at 38.97, and our acceleration is negative 9.8. So here we should get a delta y of 77.48 meters. But remember, that's just 77 meters above where we threw the rock. So to get our overall maximum height, we need to take that 77.48 and add our initial height 50. So our rock reaches a maximum height of 127.48 meters above the ground. Okay, so here, since the rock doesn't start on the ground, we need to add the initial height of the building to get our overall maximum height. Okay, so then for B, we want to see how long the rock is in the air. Again, when we're looking at the time in the air, we're going to look in that vertical direction because it's those vertical components that'll determine how long it takes the object to hit the ground. So vertically, again, we know our acceleration is 9 meters per second squared. Here, our final velocity is not 0 because it's not our maximum height, but we still have the same initial velocity of 38.97 vertical. Well, other piece of information we do know here is our displacement, okay, because we know our rock is going to end 50 meters below where it started. So our delta y then is going to be negative 50. So as always, you can use our delta y equation to solve for what that time is going to be. And again, we're going to have to use a quadratic formula. We have negative 50 is equal to 38.97 t plus 1/2 acceleration times squared. And we'll find that the rock is in the air for a total of 9.08 seconds. Okay. So then when we want to see how far from the edge of the building it lands, here we're looking for horizontal range. So we're going to use our range equation of delta x is equal to our initial x velocity times time. My screen decided it does not want to work anymore. Okay, so to find our initial x velocity, remember here we're going to use cosine because it's the adjacent side of our triangle. So 45 cosine 60, and we'll find that a horizontal component of that velocity is going to be 22.5 meters per second. So to find our range, we'll just take that 22.5, how long the rock is in the air. We'll find horizontally it travels a distance of 204.3 meters. Okay. So then D, this one is very similar to D on the previous question. We're trying to find the rock's velocity right before it hits the ground. Again, we're trying to solve for the diagonal or our velocity vector here using our horizontal and vertical components. Let me draw that a little bigger. As always, our horizontal component never changes. So if our horizontal velocity started off at a value of 22.5 meters per second, right before our rock hits the ground, it's going to have that same value. It's vertically that we have acceleration. So that's where we're going to have a change in velocity. So we know our initial y velocity, or acceleration. And we know that it's the time it takes that ball or the rock to hit the ground. So using that information, we can use our final velocity equation to solve our vertical component of that final velocity right before it hits the ground. Remember, it's not 0 right before it hits the ground, because before it hits the ground, it's still moving. So we actually need to solve for what that value is. And we'll find vertically, the rock is moving at a rate of negative 50.014 meters. Again, that makes sense that it's negative because it's moving downward. So when we put that on our triangle, now we know two sides of our triangle. So we can use the Pythagorean theorem to solve for that overall velocity, or that velocity. Again, be careful here. You'll get a positive value since it's squared, but since it's moving down, we need to make it a negative 54.84 meters per second. Okay. All right, so there was our homework on Ingold projectiles. Please let me know if you guys have any questions as you're studying for the quiz. Otherwise, have a lovely day.